All right, so this is actually still example 2, and I suppose, sorry, the A's, B's, and C's don't work very well here. Suppose this would be C. Let's go back and check. Yes, this would be C. So example 2, letter C. So same deal here. We're dealing with C14, and it has a half-life of 5,730 years. It says, if an artifact has only 20% of the C14 it had originally, about how old is it? So remembering our formula for before, we had f of x equals 100 times 0.5 for half-life to the x power. Okay, so now this is saying it's got 20% of the half-life left. How old is it? So we want to actually find out how long it took to get to that 20%. Meaning that 20% is going to, again, go in for f of x. So we have 20% over here equals 100 times 0.5 to the x power. So essentially, remember from exponential growth, we actually don't know how to solve these kinds of equations yet. We will, just not yet. Don't get too excited, because I know you are. What we have to do is we have to split this into 2. We're going to say y equals 20 for one equation, and then y equals 100 times 0.5 to the x power for our other equation. And then we're going to grab our calculators, so go get yours if you haven't had it out yet, which I certainly hope you have, because we've obviously already been graphing. And get it out, and let's go ahead. Whoops, we want to go to the y equals screen. Guess what? This is the same equation we had in there from before. So we can leave that one as is. So now y equals 20 we got to put in as a separate guy. So y equals 20. And then go back to our picture and see what we've got. Okay, that one doesn't show up, so we're going to manually zoom out again. So zoom 3, enter. Aha! It shows up now. So if you remember how to find the intersection from these, this is the same way we did it with the growth. Remember how to do it, go for it. If not, I'm going to show you one more time here. So all you have to do is go to your calc menu, which is second, and then the trace button, so second calc. You want to find the intersection, so that's option 5. We hit enter. It asks us for our first curve. Now I can't see where my cursor is. Yours might show up very nicely. I can't see mine. So I'm going to hit left and right. Oh, there's the right. And we are obviously on our exponential decay curve here. So that's our first curve. So I'm going to say, yes, I want you to take that. And it jumps to what we think is y equals 20. Aha, it is. I keep moving left and right, and I'm on that line. So we'll say, yes, that's our second curve. And then we say, yes, I want you to guess that. Boom, there's your intersection. So when there's 20% left, it's 2.32, we'll say, so 2.32 years. Now, be careful. That, remember, was increments of 5,730. So we're going to take that number and multiply it by 5,730 in order to figure out the actual amount of years. This just says, okay, take 2.32 of that many years. Okay, so let's go ahead and do that. So quit and do 2.32 times our increment of 5,730 and hit enter. So our actual artifact is 13,293.6 years old. Okay, so when it had only 20% left, that meant it was 13,293.6 years old, this artifact is. Okay, we figured out all of that using mathematics. So if I was oh shoot, I forgot the word again. Oh goodness, the people who dig stuff up. Archaeologists, my goodness, I'm thinking architect, yikes. Okay, archaeologists, I would be able to figure out, oh, hey, this skull that I found from an old dinosaur is 13,000 years old. Oh, that meant there was dinosaurs back when there was, you know, the earth was 13,000 years younger than we are now, and then I'd be able to put all the pieces together so they can use that to piece their history together, which is kind of nice. You didn't think there was any math in history, now did you? Most people don't. Okay, so now that we've been taking a look at these exponential growth and these exponential decay graphs and formulas and all that stuff. Let's sit and compare them. So we know when we had a growth model, we started out small and then it shoots up and it starts growing, 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 growing. Again, I don't like the fact that they don't put arrows on here, so I'm going to add my own to either side because it's not limited to right here. It keeps going. Okay, so we have this model, f of x equals a times b to the x power, where a is your initial amount and b is your growth factor that has to be bigger than 1. And then we say, okay, that versus decay, and I'm going to put arrows on here. And decay is just going to be essentially the reflection image of that graph, and we're going the other way. All right, so we're going the other way here, and we're losing things. So that's why we're going down as we go across time here. And we're, again, using the same formula. F of x equals a times b to the x power. This is the initial amount still. Instead of a growth factor, we call this the decay factor, and it's got to be between 0 and 1, meaning less than 100%, bigger than 0%. You can't have a negative up there. Okay. A couple things I want to point out about these graphs is you might have been thinking to yourself when we were doing 9.1 worksheet, why is it asking me so much about the domain and the range of each graph? Okay, well, let's look at the domain and the range of each graph. Remembering our domain, we squished the x-axis. So I'm just going to imagine these, remember my saw walls coming down and squishing this graph down to my x-axis. Well, what would happen would each arrow would point both ways, and I would have a domain and range. Well, I guess I could draw it in here. It would squish down to that right onto the x-axis, and we'd have a domain that goes from negative infinity. Remember, we always start in the negatives and go to the positives, to positive infinity. So our domain is going to be negative infinity to positive infinity. Okay? Now for range, remember we squish it to the y here. So this side's going to squish up here. All right? And it's going to go up forever and ever and ever. Now you have to be really careful with what happens down here, because just because this has an arrow doesn't mean it's going to squish down. I kept talking about over all of these things about how you don't ever get to 0 here. So essentially you're never going to cross the x-axis. You're never going to get quite to 0. You're going to stop right before you get to that x-axis, before you get to 0. It'll never happen because you got to take half, 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 half. You're never going to get to 0. So therefore, we're going to start at the closest thing after 0 and move on up in the positive direction. Obviously, this is infinity. This down here, we say our boundary is 0, but we do not want to include 0 because we never touch this x-axis, so we have to use a parenthesis on it. Okay, so writing your range, we'd say, okay, it goes from 0 but not touching 0. That's why we use the parenthesis to infinity. Okay, now that was for your growth. Let's see if it works the same for decay. Now decay, again, you squish it to the x-axis, you're going to get that whole range from negative infinity to positive infinity. So your domain's going to be this whole x-axis. So yep, our domain is the exact same as it was for growth. And then same for range, you squish it to the y, and this side's going up, 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 up. Oops, sorry, that was a really bad line. So that side's going up, 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 up. Now be careful, because we're never, ever, ever going to touch 0, meaning we're never going to cross this x-axis, meaning we're never going to get to 0. So we're going to stay right here, and our boundary line's going to start at 0 and go to infinity, which is exactly what our range was over here. So these are always going to have the same domain and same range here. Okay? Hopefully you remember how to do this interval notation stuff. If that was confusing to you, we need to practice it a little bit tomorrow, just because that is something, especially if you're going on into pre-calc, you're going to need to know how to do. Okay. The other thing I want to talk about really quickly, I don't know if you've noticed, but usually our x-axis represents time here. Okay, well, let's get rid of all this writing. Sorry, I'm kind of clogging up the clogging up my screen here. So we'll keep the domain and range. We want that. Get rid of all this miscellaneous business. Okay, so back to my pen. Okay, so this axis usually represents time here. And in a long time, obviously we can only go in the positive direction. We can't really control time. But when I am right here, time is what? Well, on the x-axis right here, the value is 0. So if I follow this up to where my graph actually hits, well, when no time has elapsed, what does this point right here represent? Well, if no time has elapsed, then essentially I am what do I have is what I'm starting with. So your initial amount is going to be your y-intercept. So initial amount equals y-intercept every time. And remember, the y-intercept is just where it hits the y-axis, which is right here. And so let's say we started out with 300 whatevers, then this point right here would be 0, 300. So it's your initial amount will always be your y-intercept. Same for growth. Let's say we started out with 2 bunny rabbits or whatever. So our initial amount would be 2, and that graph would hit right here at 2. So our initial amount is always your y-intercept. Okay, so these are a lot of important things about graphs. Hopefully you drew these pictures because you're supposed to have. If not, pause it and write down everything I wrote down because you're going to need to know all of these things. Okay, last example. Says, let f of x equal 25 times 3 to the x power. Find the domain and range of the function. Well, we know, okay, we have our initial amount here is 25, and our growth rate is 3 because it's bigger than 1. We know that this is exponential growth. Exponential growth. We're tripling whatever we have. So we know that the graph is going to look like so. Okay, I don't really need to even bother graphing this. I could just, pretend this is my y-axis. And, well, we're not going to ever go below my x-axis, so I had to put the x down here. So that's my x-axis. All exponential growth graphs actually behave the same. So I don't even need to graph this specific function. Once I identify that it is exponential growth, I can just use the model in order to determine my domain and my range. So domain and range, please write these in interval notation. So your domain, remember we squished to the x-axis, that's going to flatten out here, and it's going to be from negative infinity to infinity. And our range, remember this side will flatten over here, so it's going to end up going straight up, but this side down here, never ever 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 gonna get to 0. So it stops, like with brakes, it stops right before it gets to 0. And, you don't want to say, oh, well, Miss Warner, doesn't it start at 1 then? Well, no, you're right. 1 is not 0. But what about 0.5? What about 0.25? What about was 0.0000001? You can't eliminate any of those things. So you have to say, okay, well, we're not going to start at 0, but we're going to start as close as we can to 0. That's why we say 0 not included. And then we're going to go to infinity. Okay, so 0 is going to be what we're allowed to get close to, but we're not allowed to touch it, as indicated by the parentheses here, to infinity. Okay, so there's our domain and our range for this equation. Like I said, I didn't even have to graph this out. Once I recognized it was exponential growth, they all behave the same way. So I could just conclude that that is my domain and that is my range. If you don't believe me, go ahead and graph it on your calculators and you'll see the same thing. Alright, and that is actually all we have for exponential growth and decay. So hopefully you got a good grasp on those models, those graphs, how they all behave. And if you have any questions, please make sure you ask me in class tomorrow. Have a good night, Algebra 2.